Chapter 10 Magnetic Field due to electric current. Next topic, axial magnetic field produced by current in a circular loop. We consider circular loop, and this circular loop is in axial magnetic field, that is x-axis, y-axis and z-axis. There is three-dimensional case, and in such case the two axes is xy or xz or yz is the plane of such circular loop, and one axis, suppose z-axis, is perpendicular to that plane, and we consider any point along any axis, that is x-axis, y-axis or z-axis, and we find out that point the magnetic field produced due to this coil or circular loop carrying a steady current. Now we consider a circular loop. This circular loop carrying a steady current I, and his center is O. We consider a circular loop carrying steady current I whose center O. Also, we consider z-axis, which is z-axis perpendicular to this circular loop. Another suppose this is y-axis, this is suppose x-axis. This is the center, and we consider DL is the small length element. Also, DL is the small length element. And we consider a point P. Consider point P at a distance z from center O along z-axis, and join this length element and point P. Suppose this angle is theta. Join point P and length element, and suppose this distance is small r bar. In figure, this circular loop carrying steady current I whose center O, and suppose capital R is the radius of that circular loop, and this dl is the small length element at that point, that is along z-axis or y-axis, and a point P along z-axis at a distance z from center O, and we find out the magnetic field at point P. Magnetic field at point P. Suppose this vertical component, this is the D Z. Suppose this is the magnetic field at point P along the direction of Z axis, and this is the magnetic field dB bar perpendicular to Z axis. Suppose this is the resultant magnetic field, and suppose this angle is theta. The diagram is complete. Then we find out the magnetic field or total magnetic field at point P. Now we consider circular loop carrying steady current I, and O is its center. Also, capital R with a radius of circular loop. DL with a length element. Point P at the distance Z from point O along Z axis. At point P, the dBz magnetic field or magnetic field induction along the Z axis, and dB perpendicular this along the perpendicular to Z axis. But this dB perpendicular is also perpendicular to this dB perpendicular is perpendicular to DL and R, hence the dB perpendicular is 0. Only dBz and dB is remaining. Then find out the magnetic induction at point P. Before we used Biot-Savart law. This is the explanation, small explanation of that figure. Now we consider or we used Biot-Savart law using Biot-Savart law. dB is equal to mu 0 upon 4 pi I dl cross r bar divided by r cube, or this is written as dB is equal to mu 0 upon 4 pi I dl r divided by r cube. This is equal to mu 0 upon 4 pi I dl divided by r square. dB is equal to mu 0 upon 4 pi I dl upon r square. So equation number 1, this is the Biot-Savart law. And we will find out the magnetic field at point P, but we find out dB perpendicular is neglect, or that is 0. Only dV Z is equal to dP cos theta. This is the magnetic field at point P. But in figure, the value of cos theta is equal to R upon small r. Now find out value of small r. In triangle OP, or suppose DL, the R square is equal to under root Z square plus R square, and R equal to under root Z square plus R square. Therefore cos theta is equal to R divided by under root Z square plus R square. We get first equation, dV is equal to mu 0 upon 4 pi ideal upon R square. Using Biot-Savart law, dV Z is the magnetic field along the Z axis. dV cos theta is equal to dV cos theta, and cos theta, using this triangle, the value of cos theta is R upon under root Z square plus R square. Now we consider the total or net contribution along Z axis by integration, by taking integration of that dVz, then we get the net or total magnetic field at point P. And suppose that magnetic field along Z axis is suppose Bz. V is magnetic field along Z axis, hence we can write Bz is equal to integration dBz. But the value of dBz is equal to integration dB cos theta. Therefore Bz is equal to value of dB is mu 0 upon 4 pi I dl upon R square into cos theta. Bz is equal to integration mu 0 upon 4 pi I dl value of R square under root Z square plus R square, and value of cos theta R divided by under root, value of R square is Z square plus R square. Therefore Z square plus R square, or value of cos theta R upon Z square plus R square. Therefore Bz, that is magnetic field along Z axis, is equal to mu integration mu 0 upon 4 pi I R into dl divided by Z square plus R square raised to 3 pi. Now Bz is equal to mu 0 I R divided by 4 pi or z square plus r square raised to 3 by 2 is constant integration dl. But integration dl, this is very small element. If we take integration dl, we get total circumference of that circular loop. And we know that the total circumference of that circular loop is c, or this is circumference of circle, and its value is 2 pi, radius is capital R. Therefore, using value of dl, then dz is equal to mu 0 I r into 2 pi r divided by 4 pi into bracket z square plus r square raised to 3 by 2. And finally, we get this pi get cancelled, 2. Therefore, Bz, that is magnetic field produced by circular loop along z-axis, that is Bz is equal to mu 0 I r square divided by 2 into bracket z square plus r square raised to 3 by 2. This is the final expression of that magnetic field, or this Bz is denote the magnetic field or magnetic field induction at point P along z-axis is equal to mu 0 I r square to z square plus r square, where Bz is magnetic field induction, this is constant, I means current, r means radius of circular path. This is the axial magnetic field produced by circular loop along z-axis.